Thanks for coming. My name is Warski, and there's a recent trend, at least I think so, that free monads are getting quite popular, at least in the Scala land. I guess they have been popular in Haskell for quite a while. And it wasn't always immediately clear for me what this free means when it's applied to monads. So I will try to explain today, hopefully, what's the intuition behind free and how can we understand free. So it's going to be a bit of an experimental talk for me because it's going to be mainly math. So we are continuing the theme of the previous talk. There will be a bit of code. And as always, if you have any questions, just let me know if something is not clear. OK, so our overall plan. First, I will try to sell you some motivation of why should we consider using free monads in the first place. That may not be obvious. It's not needed to understand free monads to understand the talk, but being motivated is usually good anyway. And then I would like to introduce 5 basic concepts from universal algebra, from math, that will get us to free monads. They are quite simple concepts. They're usually formalizations of what we do every day. So even if they have big, scary-sounding names, don't worry and don't look for a deeper meaning. Things are really simpler than they sound, and they're just formalizations. So after we get to free algebras and free monads, we will also take a short look of how free monads are implemented in practice in Haskell and SCALAZ. So what I would like to show overall is that free is a general construction which you can apply to many different structures, not only monads. OK, so why would we want to bother with free in the first place? I tried to state the problem that we are trying to solve when using free monads. Maybe there's another approach to it as well. But at least how I understand these things is that we want to be able to define programs in a composable way. Composable meaning that we want to build bigger programs from smaller programs. And we want to use some business-oriented language, so some high-level instructions, without giving specific machine interpretation of what these instructions mean. So we want to define a program in a high-level language, and we only want to later specify of what these high-level instructions actually do and how they translate to specific operations on the database and so on. So once we have this program defined, we want to be able to run it in context. Okay? So as a very short example, again, I don't want to give this talk to be an introduction to free monads because it will be a whole talk in itself. As a very short example of what a free monad can look like, in the code snippet below, we see a function which returns a data structure called free. The first type parameter of the data structure describes the possible operations that we can use when writing our program. And the second type parameter, credit limit, is the type of the result of the whole program. Okay? And here we are, our program will be represented as data, which will allow us to manipulate it later. So the instruction set here are the bank ops, and to issue a credit card to a user, we are using these operations which are looking up user data, fetching the user's credit history, calculating the limit, and so on. Okay, so these are our basic operations, and we are combining them using the monad syntax. As a result, we are getting a data structure free. So hopefully we'll understand why free is called free after this talk finishes. So what we get is we get a description of how our problem should be solved, okay, without any specific interpretation. So there's no interpretation of what looking up user data actually means. Okay? It's just an instruction, look up user data. It's just a piece of data. It doesn't mean anything yet. And then we can write interpreters for our instructions, which will actually run some real operations. So for example, here we have a production interpreter, which interprets our operations in terms of a future. Right? So for example, here looking up the user data would actually mean going to the database and fetching something from the database, which is a side-effecting operation, so we wrap it in a future. Okay? We can also create another interpreter, for example, a test interpreter where we don't, where we want to only test the logic. We don't want to test the integration with the database. So here we just interpret each operation as a strict value without wrapping it in anything special. And once we have an interpreter, and once we have our data structure, the free monad, which wraps our program description, we can actually interpret it using an interpreter and get the result. Okay? So that's like a very brief introduction to free monads. There's a lot of learning material on the net. If you weren't familiar, maybe this got you interested in how this actually works, the monad syntax and so on. So there's a lot of plenty material, a lot of learning material on the internet, which explains it in detail. So what I would like to focus on here is what is the meaning of the word free and where it comes from. Okay, so before we start doing that, just a short introduction who I am so that you know who's talking to you. So I'm a software engineer and the co-founder of Software Mill. We are a small company based in Poland. We do custom software for various types of clients, startups, banks. We do all kinds of messaging systems and so on. I heard we are a company of nerds. I don't know how could anybody think that. Just look at me. So I do mainly Scala. I do some open source projects such as QuickLens, McQuay, and so on. And what actually inspired me to do this talk is a long time ago in my previous life, I was a student of category theory. So that's where I learned these things, and I hope I will be able to pass some of this today. Okay, so let's start with actually defining what is an algebra. Okay, so if we go to Wikipedia, the ultimate source of all knowledge, you can see that algebra is the study of mathematical symbols and the rules for manipulating these symbols. Okay, so we have a set of symbols that we can arbitrarily choose, and then we define some rules of how they can be manipulated. And in fact, we see a lot of algebras in our everyday life. Maybe not every day, but almost everyday life. So some simple examples like the linear equation, right? We have some symbols, y, x, a and b plus, and there are some specific rules on how these can be manipulated, right? It's an algebra. It can get more complex. We can invent our own symbols and so on. Going further, we can even go quite crazy and define some symbols like this, right? This is still an algebra. We are quite good at manipulating these specific kinds of symbols, right? We know the rules quite well. If we forget the rules, the IDE usually corrects us. So these are all examples of algebras. But now we will go a level higher and we'll try to abstract from the actual specific symbols used. And that's where universal algebra comes in. And that will be the first thing I would like to introduce, the first concept. It will be of an algebraic signature, okay? In universal algebra, what you do is you don't study specific algebras and specific sets of symbols. You just say that you have some symbols and you see what you can do with this notion, okay? So universal algebra studies more general studies any algebraic structures rather than specific ones. So to define an algebraic signature contains of two things. It's usually denoted as a large letter sigma. It consists of a set of type names. Okay, these are just labels, just names like strings, nothing special. A set of labels, which are a set of type names. Here we will deal with a multi-typed universal algebra because we all like static typing. And then there's a family of sets of operation names. Okay, the operation names are indexed by a series of types names and one additional type name. Okay, so the series of type names are the types of parameters of an operation, and the second one is the return type. Okay? So in an algebraic signature, we have a set of type names and some operations. So as an example, which we will use later on as well, we can have, for example, two type names, int and string. Again, these are just labels. They don't really mean anything. You kind of can guess what they might mean, right? Because int and string are something that we use every day. But here they are just labels, okay? Two labels. And then we have some operations, okay? We have one operation without any parameters and a return type int, which makes it a constant, which is 0. Again, it's just a name, no interpretation, okay? It's just a name. Then we have an operation which takes an int and returns an int, called a successor. We have another operation which takes two ints and returns an int, called plus, and so on. Okay? So that's an example of a signature, right? We have a set of type names and a family of sets of operation names. And we can build expressions using using this signature. Okay? We can also define like a signature for Scala or for Haskell, right, and build programs as well. Now, the second concept will be an algebra. Okay? We have an algebraic signature which specifies the symbols that we can use, our language, right? And now we want to actually have a specific interpretation. Okay? And an algebra is a specific interpretation of a signature. So an algebra consists of two things again. So for each type, it assigns a set of values. And for each operation, it assigns a function between the appropriate sets. So again, following our example, that's the same signature as before. Now we can define an example algebra A. Okay? Our algebra, there's a lot of possibilities of how we can define this algebra. There's only one of them. So in our algebra A, the interpretation of type int will be natural numbers, and the interpretation of type string will be the set of all possible strings. Okay? That's one way we can actually interpret this signature. So we have an interpretation of the types. We also need an interpretation of the operations. Okay? So here we say that the successor in algebra in algebra A, so it's the successor with the A suffix, is a function which adds 1 to its argument. Okay? We can define it like that, why not? And similarly, we define plus in algebra A, and so on. Okay. So that was the second out of 5 concepts that we need to introduce to get to free algebras. Now, we will define a special algebra called the term algebra. So we will define this algebra for any signature. Okay? So this algebra will be it will be quite boring. So it will consist, the interpretation of each type will consist of all well-formed expressions of this type that can be built. Okay? So the elements in this algebra will be strings built out as expressions out of the operations that we have. Okay? So it will be an algebra built out of pure syntax. Again, no special. There will be no like special interpretations. We'll just build an algebra out of pure syntax. You can think of it as an algebra containing valid code using our signature or well-formed strings and so on. So as an example, we have our example signature as before, and now we define the term algebra T sigma. Okay, sigma is references the signature, and T is like term algebra. Okay, so first we have to define the interpretation of the types. Okay, so the interpretation of type int is all expressions that we can build using our symbols that have type int. Okay, so it's 0 obviously. It's also successor applied to 0, right? Successor 0, and so on. And similar with type string, right? It's all expressions that have type string. Now we also need to provide an interpretation of the operations. Okay? So the operations, again, they're quite boring. So the interpretation of the successor operation in our term algebra will just build a bigger expression, a bigger string. Okay? So on the left, where you have the successor T sigma, that's a function, an operation interpreted in the term algebra. And on the right, you have a term, right? So it takes a term and it returns a bigger term, which is the successor applied to the old term. Okay? So as our interpretation of the operations, we just built out bigger expressions, okay? So it's an algebra built out of all valid expressions built using our language. And another way to think about the term algebra is that it is defined inductively, okay? So as the induction base, we take all constants that are available in our signature. So here it will be only 0. And then on each step, we apply any functions that we actually can apply to the terms that we currently have. So we start with a 0. So we can only create 4 terms out of a single 0 in the next step, right? We can add 2 zeros, we can create a successor of 0, and we can convert a 0 to a string. In the next step, we get more terms and more terms and more terms, and if we sum it all up, we'll get the term algebra. Okay, so that was the third. We have the algebraic signature algebra and the term algebra. We are halfway there. So now a homomorphism. So now let's say we have a single fixed signature, and we have 2 algebras, 2 different interpretations of the same signature, okay? And we want to be able to somehow relate these two algebras. We want to create like a function between the algebras. And that kind of function is called the homomorphism. Okay, it's nothing special, it's just a name for a function between algebras. And a function between algebras, it's kind of what you would expect. So for each type, we need the function between the type interpretations. Okay? But these functions cannot be arbitrary. They need to be well behaved. And I will show by example what this means. So again, we have the same signature. Let's say we have two algebras, 2 interpretations of our signature. Okay? And now we say that a function is a homomorphism if there are 2 functions. So there's a function between the interpretation of ints, and there's a function between the interpretation of strings, such that the operations are preserved, such that the functions are well behaved with respect to these operations. What this means, for example, if we take the successor one, right? If we map the successor of any value in algebra A, it must be the same if we take the successor in algebra B to the mapping of X. Okay? It means that we can pull the operations outside of our homomorphism of our function. Okay? It's kind of, if you try to think it a bit, it kind of is what you would really expect from such a function. So that's the definition of a homomorphism. Okay. And now the final thing that we need to introduce is the notion of an initial algebra. So that's almost the definition of a free algebra. Okay, so now it will be a definition. It may be a bit hard to digest, but don't worry, it's just a definition. So we will say that an algebra I is initial. So it will be a special algebra. Okay, a very special algebra. It will be initial. And in fact, you can hear about initial objects, for example, when reading about Haskell quite a lot. So it's the same initiality. So we will say that our special algebra I is initial. Then if we take any other algebra A, and that there will be exactly one homomorphism between I and A. Okay, so that's quite a strong requirement. So for any other algebra A, there must exist a homomorphism between I and A, and it must be unique. Okay, and now there's a theorem that actually our term algebra is initial. Okay, so why is that? Of course, the proof is an easy exercise to do at home, but I will do a proof by example, which I hope will convince you. So we will take our example signature, and we will take our example algebra A. If you remember, in that algebra we interpreted ints as natural numbers and strings as all possible strings, right? So it's like quite a natural interpretation of this algebra. So now to prove that T sigma is initial, we have to construct a homomorphism between the term algebra and our example algebra A. So we need to construct a homomorphism F. Okay? So now how can we construct such a homomorphism? So most of the construction follows from the fact that it needs to be a homomorphism, and so it needs to preserve operations. If it needs to preserve operations, then for example, it needs to preserve the mapping of the constants, right? So the 0 interpreted in the term algebra, so the term 0 must be mapped to the interpretation of 0 in algebra A. Similarly, from the fact that this is a homomorphism, the mapping of a successor of the term, of the successor of any term must map to the successor of, in algebra A, of the mapping of that term, okay? And so on. So, because the term algebra is defined inductively only from the symbols that we have at our disposal, you can see that there's only one way to actually build that homomorphism between the term algebra and algebra A, okay? And that homomorphism, in fact, is an evaluation of that expression in algebra A, okay? So we take any term, so we take any valid string built out of our language, okay? And we interpret it in algebra A, okay? And that's our homomorphism, okay? And we can always do that. For any algebra A, we can take any valid expression built out using our signature and interpret it, run it in our algebra A, right? Okay. So our term algebra has two important properties which carry over to free algebras later. So first of all, an initial algebra, a term algebra, it contains no junk. So it contains only the elements which any algebra for that signature has to contain. Okay, so it doesn't contain any extra elements, right? It only contains, because it contains expressions that can be built from our language, it doesn't contain any extra elements, right? So there's no junk, and it doesn't confuse if two terms might, in theory, have different values in interpretation, they will be distinct terms. Okay, so to show counterexample, I will show that our example algebra A is definitely not initial. Okay, so if you remember our algebra A, we interpreted ints as natural numbers and strings as the set of all strings. So it contains junk because, for example, the string A is not reachable by any expression, right? It also contains confusion because in algebra A, 0 plus successor of 0 is the same as successor of 0 plus 0. But in general, it doesn't have to be. We can build an interpretation of the of our signature. We can build an algebra such that these two terms have different values. Okay. So finally, we reach the free algebra. But to do that, we need to add a small twist to our definition. So now we will define terms with variables. Okay? So far we had just terms built out of our language construct, right? out of the signature. And now we will take a set of variables. Each variable will have a type, okay? And we will build expressions using our language with these variables added. So for example, if we have our example signature again, we define the set of variables x. So we have 3 variables of type int, ijk. We have 2 variables of type string, s1 and s2, okay, as an example. And using these variables, we can build expressions, okay? Of course, well-formed, the types must match. So for example, we can build an expression, successor of I plus j plus successor of 0 or something like that, okay? So T sigma from T sigma x will denote our term algebra built using a given set of variables. Okay, now there will be a very hard definition, but we will make it simpler later. Okay, so now we will say that, again, a special sigma algebra I is free over x. Okay? When you say that something is free, the parameter of the x parameter is important, and here it will be the set of variables. Okay? So we say that our special algebra I is free over x when, if we take any other algebra A again, and if we have a mapping of the variables, so if we have an interpretation of the variables this extends uniquely to homomorphism between the algebras. Okay? So that may sound complicated. We'll see what it means in practice in a second. Okay? And of course, you probably expected it, that for any variable set x, our term algebra built with these variables is actually free. Okay? And that is the same free as in free monad, and we will see the connection in a second. So what this definition really means is that if we have a target algebra in which we want to interpret our expression, right? An interpretation of the variables determines the interpretation of the whole term. Okay? So the interpretation of the variables is the function f between our variables and our algebra, and the interpretation of the whole term is our homomorphism, the f sharp. Okay? So as an example, we take the same signature as before, the same algebra as before, and we define an interpretation of our variables. So we say that an interpretation of I is 10, and the interpretation of j is 5, and then the interpretation of s2 is days. So now we can interpret any expression built out of our language using these variables, right? So this f sharp is just an evaluation of this expression in algebra A, okay? And it's quite straightforward, right? It's more or less what you would expect, right? So if you take the successor of j, it will be, in algebra A, it will be 6. Then you add 1, so it's 7, and so on, okay? Okay, so now, what does it really mean that this algebra, this term algebra, is free, okay? So it means two things. First of all, it's if we take first of all, it doesn't provide any interpretation in itself. Okay, the elements it contains are free to be interpreted in any way. Okay, that's one aspect of the freeness. Okay, there are no constraints. You can interpret the elements in any way. Okay, it doesn't do any interpretation itself. And secondly, it's free of any additional structure. It contains only the structure that it must contain because our signature told it so, right? So it's free of interpretation and free of additional structure. And that's the two aspects of freeness, of why it's actually called free. As I said, it's a free algebra contains no junk, so there are no extra elements, and doesn't confuse any two elements if it doesn't have to. Okay. So just to do a short summing up of what we said so far. So we introduced an algebraic signature, which consisted of a set of type names and a family of operation names. Then we said that an interpretation of a signature is called an algebra. Then we have defined a term algebra, which are valid expressions built out of using this signature, right? It is kind of what we do every day, right? We have a signature, our language, Scala, Java, whatever, and we build valid expressions using this language, hopefully valid expressions using this language, right? And then we interpret, so our interpreter is our machine, which actually interprets our compiler, which actually interprets our terms into something more meaningful to the computer than a text file. Okay, and then we said that the term algebra is free, right? It is free if an interpretation of the variables that it contains determines an interpretation of the whole term. Okay, and it's a it's a general construction which you can apply to any algebraic structure, to any algebraic signature. Okay, and you can get a free algebra. And that term algebra is free, meaning that it is free of, it doesn't interpret anything in itself. It's free of additional operation, interpretation, and free of additional structure. Okay, so now let's get to monads. Why would we look at monads in the first place? So let's put free aside for a second. So now, following our original motivation of why we want to look at the free monad, we said that we want to model programs as data. Okay? So in any program, so if we want, any way we approach the task, any way we approach the task of modeling program as data, we will, a sequential program for now. We'll always need two operations. An operation to return a value, and an operation to compute what to do next based on the previous value. Okay? So these two operations will be always there, whatever your other basic operations are. So people decided, no, if these operations are always there, why don't we extract these common parts, right? We all like to extract common parts and abstract them, right? So let's extract these common parts and give them a name, right? And they couldn't think of a better name, so they came up with monad, and that's what we are stuck with now. So a monad is just really these two operations, these two common operations that are extracted so that we can model sequential programs, right? There are also some sanity laws in monads, right? So that they behave well. So they're like added in addition to the basic monad structure. Okay. So now that we know we want to use a monad more or less to model our program as data, because people decided that it's a good abstract way of modeling programs, of modeling sequential programs, how would we approach the free monad? So the free monad, now that's not a direct construction, it gets a bit more complicated, but a very rough sketch would be that in our signature, we have pure and flat map, right? We have two operations. The variables will be our basic operations, our DSL, that will be our variables. So if we define the signature and the variables in such a way, the free monad will be more or less all the terms, right, like just data structures, terms, built out of pure flat map and our variables. Okay? And that's more or less what the free monad is. Of course, we have to add. So I said that in a free algebra there is no confusion. Here we need to add some confusion to satisfy the monad laws. Okay? So the free monad still has to be a monad, so it needs to introduce some confusion, but only as much as is needed, right? So for example, here is one monad law, right? That flat mapping a pure value with a function is the same as applying the function to that value. So it will need to actually confuse these two terms. Okay. So you can actually do this construction yes, and an important thing that follows from our definition of what free means is that if we provide an interpretation, if we pick a target monad, right? Before we picked a target algebra, now we pick a target monad, okay? And if we provide an interpretation of the variables in that monad, okay, that extends uniquely to an interpretation of the whole program, okay? That's exactly the same as with free algebras. To get a bit more precise of how you would actually construct the free monad in such a direct way, okay, so we would need to tweak a bit our construction that we did before. So before we were dealing with algebras, so our world were all algebras, right? Here we will have to switch our world to all Scala or Haskell or whatever monads, okay? And switching this world is doing these calculations in a different category. Also, we have to switch the world of variables. Before, we only used sets, and now we will have to use valid Scala terms, right? So, for example, to define the DSL, right? That's usually some data structure, so that's a valid Scala term. Okay? But otherwise, the construction of the free monad goes more or less similarly. And now, if you look at how free is defined in CATS or in SCALAZ, you will see that it is a data structure. Okay? So one important thing about the free monad is that it's just a data structure. It's nothing special, just a data structure. Okay? So there's a data type free. As I said, the first type parameter is the type of the operations. The second type parameter is the return type of the whole program. So it contains three constructs. Okay? So we have pure and flat mapped, which are a direct reification of the pure and flat map monad operations, right? So that's, you can see that if we build a data structure using free, we actually end up building a big term containing pure and flat map, right? So our signature operations, let's say, but it also contains suspend. So suspend is simply an embedding of our variable, of our DSL, into the free data type, okay? So in this definition, we have a reification of two operations, of the two signature operations, right, as terms, and we have an embedding for variables, which is for value from our DSL. So that's more or less what we have. It more or less follows the construction that we did. Now, if you go to actually Haskell and take a look at the Haskell definition, it is a bit different. Okay, so I've translated it into Scala as well. So in the Haskell definition, you have an additional requirement that f must be a functor. The first type parameter must be a functor, and you only have two constructs: pure and join. Okay. Well, pure is quite clear, but what's that join? Well, it turns out that these are luckily equivalent, so it's the same free monad in Haskell and in SCALAZ and in CATS. And you can translate between the two forms, okay? What is the difference is that if you look at this representation, because of monad laws, you can have the same expression represented by two terms, right? So an equivalent expression represented in two ways, right? For example, if you have a series of flat maps, you can have a left-biased, a series of flat maps, or you can, using the monad laws, the equations, you can put all the flat maps on the right, right? Or you can apply the simplification, flat mapping a pure value, and so on. So for some expressions, there are two ways you can build a term to represent that expression. And this form that you can find in Haskell is kind of normalized. So each expression has only one form. And when you actually do the translation, if you have a free expression written in that style, if you do the translation to the Haskell style, let's say, you will see that you actually normalize your expression so that it has only one form. Okay. An important note is that the f over here, so the type of the DSL, is different than the f over here. Okay, the f in this representation has to be a functor, right? And it doesn't have to be in the other one. So what we do is we can actually make any data container a functor by creating a pair data container plus mapping function. Okay, that's quite a simple operation, right? And that again, actually, is a free functor built out of our basic data container, which doesn't have to be a functor in the general. It's called a Coyoneda, again, a fancy name, which just means a functor with a mapping, a data container with a mapping function, right? So in Java, you would have probably a container with mapping or something like that, and in Haskell, we have a Coyoneda. It's a name as any other. Okay, so to sum up, so what we did is we did a direct construction of free algebras using basing on any algebraic signature. We kind of a bit transpose that to constructing a free monad. The free monad that we constructed is again why is it free? So the expressions that if you have a data type which represents a program, right? That program can be interpreted in any way given the interpretation of the variables, right? So you are free to interpret it in any way, and there's no additional structure. Okay, so that's more or less what we went through. If you would like to read some more about it, there's a book from which I learned the universal algebra and category theory. It's by one of my Advisors, I guess it's called. So it's a very nice book. It contains a lot of exercises. If you'd like to find out more about category theory, for example. And of course, the internet is an endless source of reading material, YouTube videos, and so on. Okay, so that's all I had. Thank you very much.